So we're continuing on with the periodic table, and eventually what we want to be able to do by the end of this unit is to be able to predict properties of a particular element based on their position on the periodic table. And not only predict them, but then maybe explain why are certain elements more reactive than others. And a lot of it has to do with the electron structure. So the nucleus is cool, protons, neutrons is great. But until we talk about nuclear reactions, we're going to kind of put the nucleus on the back burner for a while. And really, chemical reactions and chemical properties are all a result of the outermost electron structure, the valence electron structure. I mean, all electrons are important, but when you think about two atoms interacting with one another, it's their outermost electrons that are going to interact first. And so some of this we already know, right? We already talked about the patterns that exist on the periodic table, and we already know about the S block. And the S block here being in yellow, it's the first two groups going up and down because the S orbitals hold 2 electrons. We already know about the P block going across 6, not starting till the second energy level, because really, I mean, helium has an identity crisis, and helium's not really going to end P6. Helium doesn't have 6 electrons. We know about the D block starting in the third energy level, going across 10 electrons or 10 elements, and the crazy F orbitals that are really mostly radioactive and synthetic elements. We kind of know this, but this diagram here gives us a nice visual of the valence electrons. Valence electrons are going to be our top priority when we're trying to predict some properties of these groups. And so here they just pulled out 4 of the groups. We've got the alkali metals and the alkaline earths that fill the P block. And so everything in the alkali metal group, group 1, if I look at their electron configurations, and here they've got them in the noble gas shortcut, because then you can clearly see the valence electrons, and they're the most important. The core electrons are what we're really just shortening by putting in like neon. Well, when I say neon, I mean 1s2, 2s2, 2p6, and those would be the core electrons anyway. And yes, they're important, but they're really not going to be involved in bonding or reactions. It's that outermost energy level that I'm most concerned with. And so do you see what happens if you look at the configurations going down the group? They all end something S1. Lithium is 2s1. Sodium is 3s1. Potassium is 4s1. And so we looked at some of the alkali metals, and they have kind of wacky properties in that they're metals, but they're soft and they're crazy reactive. Does that maybe have something to do with the fact that they all have 1 valence electron? Like, what would that mean? Like, I wonder eventually what having 1 valence electron does to the properties. Like, why would that make these guys really reactive? Eventually we'll figure it out. And then as we go down the group, we saw that the properties just intensify. That, I mean, all of these alkali metals react with water, which is funky in itself, but then to go down the group and see that they get more and more reactive, well, the difference is just that the outermost electron is in a higher energy level. So eventually I want to know, like, is there something about the electron being in a farther energy level, like farther from the nucleus? Does that maybe have something to do with the elements becoming more and more reactive? That, like, lithium has its outer valence electron in the 2nd energy level, but like cesium would have its outer electron in the 6th energy level. I wonder if that has something to do with the fact that as the electrons are farther from the nucleus, the properties intensify. The alkali metals get more and more reactive. If you hop next door to the alkaline earth metals, they're all going to have 2 valence electrons. They'll all end something S2. Oh, cool. And again, if I had samples of all of these elements, they do get more reactive going down the group. Just kind of like the alkali metals, they're just not quite as crazy. I mean, they don't burst into flames, but they fizz and bubble and give off hydrogen, which is kind of fun. Then if I hop across to the P block, I mean, they've only pulled out the halogens and the noble gases. But for example, let's say I were looking at boron. And so boron would be right here. And so boron's electron configuration would be, if I do like the noble gas shortcut, I'd go backwards to helium. And then I'd be 2s2, 2p1. Valence electrons are all the electrons in the outermost energy level. So I have a total of 3. And that would be the same of everybody in that group. We don't have a fancy name for them. We just kind of call it the boron family. Everybody in the carbon family would have 4 valence electrons. Everybody in the nitrogen family would have 5. Everybody in the oxygen family would have 6. And then you get over to the halogens and noble gases. And they'll all end, in the halogen group, something P5. The noble gases, besides helium, will always end something P6. And again, the difference is just that the P orbital is a larger orbital. Or it's an orbital that has electrons farther from the nucleus. The energy level increases. But I'm going to mark this in, and I'm just going to remind myself that everybody in the first group has 1 valence electron. Everybody in the second group has 2 valence electrons. I'll put this up here. These are valence electrons. Eventually, it's really important to be able to predict how many valence electrons are in a particular atom. If you were to go across to the boron family, everybody has 3 valence electrons, and so on. When you get over to the fluorine, the halogens, all of the configurations, yes, end something P5, but I'm also going to put in that there's going to be S2. There's going to be something S2, something P5. So like fluorine is 2S2, 2P5. Chlorine is 3S2, 3P5. They all have 5 valence electrons total. And even when we get to like bromine, we want to look at all the electrons in the outermost energy level. And so we kind of mentioned that there are different ways that you could organize these orbitals. Often with bromine, I would have written this in the order that the orbitals fill, where I would have put argon, and then 4s2, 3d10, 4p5. That's normally how I write it. It's totally fine that they've rearranged them a little bit here, because what they're trying to show is the valence electrons. They're the electrons in the highest energy level, which is the 4th. So it's these guys and it's these guys. These are my valence electrons. Highest energy level in bromine would be the 4th. And so when you get through like the D block, the D block will never be counted as valence electrons because they're always in like 1 energy level lower. But there are a total of 5 still. And same thing, when we get over to the noble gases, it's always going to be something S2. Whoopsies. Did you catch my mistake? Oh my gosh. Brain fart. 7. 5 and 2 is 7 valence electrons. 7 total. And then when you get over to the noble gases, 2 and 6 is 8, except for helium. Technically, helium only has 2 because he's just filling the 1s orbital with 2 electrons. So the valence will be all the electrons in the highest energy level. But I can totally see that with these electron configurations in the noble gas shortcut. These are my valence. These are my valence. When I get to krypton, it's anything in the 4th level. Xenon, anything in the 5th. Radon, anything in the 6th, and so on. And there's something about the electron structure being similar that's going to give us similar properties. Okay, and that's kind of what they're getting at here, that we want to be able to model the arrangement of the electrons in the energy levels. And so here's a sodium atom, and this is kind of what we mentioned in that by using the noble gas shortcut and saying neon, neon represents your core electrons. These are my core electrons. And they're all in nice full orbitals. Every S has 2, every P has 6. They're really stable. The valence electron then is my outermost electron, my most important. So here's my one valence electron. And so number 8 wants us to create a model, a science and engineering practice. Use a model. Use chlorine's position in the periodic table to draw a model of chlorine that includes the nucleus, core electrons, and valence. So kind of similar to what they've done with sodium. I'll even try to match the colors. Okay, so nucleus. And they didn't really mention like how many protons and how many neutrons. So I guess I won't either. But I'll label this as my nucleus. Okay, so there's my nucleus. Then I'll try to do it really similar. I'll do the first energy level. Okay, so the first energy level of chlorine, 1s, right? 1s2. And then that's it for the first energy level. I'd hop to the second energy level. In the second energy level, I'd have my 2s2 and my 2p6. Fantastic. And then I'll go kind of orangey color. Whoa, baby. Okay, here's my third energy level. So now chlorine, I'm looking at my periodic table. It's number 17. So I'm going to have to go 3s2. And then I'm going to have to hop across to the 3p. 1, 2, 3, 4, 5. 3p5. And so these would be my core electrons. All of these guys that are in nice full orbitals, those are my core. And then my outermost electrons are my valence. My valence electrons. I'm going to put this as core electron. There we go. And so eventually we want to be able to kind of model the valence electrons in any atom based on their position on the periodic table.